Many electric devices are used in an automobile, and electricity seems to be difficult to understand because it is not visible to the eyes. In this video presentation, therefore, we will study electricity in visible ways. Electricity is often compared to a flow of water. In fact, we will see how water flows first. Water runs from a higher place to a lower place. Electricity also flows from a higher to a lower place. The difference in the water level between two places is called potential difference or voltage in electricity. The amount of flowing water is called electrical current or simply current in electricity. Now, watch what will happen to the speed of the wheel. When you squeeze the pipe, the wheel starts to rotate at a lower speed. Something that disturbs a smooth flow of water like this is called electrical resistance, or simply resistance in an electric circuit. Now, we will do a little experiment to study basic relationships in electricity. First, we'll study the relationship between voltage and current. Let's measure the voltage of this battery using a voltmeter. A voltmeter is connected to both ends of the battery, or anything you wish to check the voltage of. The voltmeter indicates 13 volts. The volt is used as the unit for voltage, symbolized by V. The bulb goes on. The bulb lights up because current is flowing through it. Current flows from the positive terminal through the bulb and to the negative terminal of the battery, just as water flows from a higher to a lower place. You can check the flow of current with an ammeter. An ammeter is connected along the current's path. The ammeter indicates 0.4 amperes. This shows that 0.4 amperes of electric current is flowing through this circuit. The size or amount of current is measured in amperes, symbolized by A. Now we will continue our experiment using two batteries. The voltmeter shows twice as high a voltage as before. Let's check what happens to the current. We connect the same bulb and ammeter as we did before. The bulb is now brighter than before. The amount of current is also greater than before. From these experiments, we learned that more current flows through a circuit when we increase the voltage without changing the bulb or the resistance. This can be demonstrated using the model of a water mill. When the water level or voltage is higher, more water or current flows. In the case of the water mill, the wheel turns at a higher speed. Now we will study how resistance affects current. We take electricity from a 13-volt battery. we connect a bulb and check the amount of current. Now, what will happen to the current when we connect two bulbs? The amount of current has decreased. This experiment shows that the amount of current decreases as resistance is increased, and that current increases when resistance is reduced. Resistance is indicated by a unit called the ohm. Now, you know the relationship between resistance and current. Let's summarize the relationship between voltage, current, and resistance. When we connect a resistance of 3 ohms to a 12-volt battery, a current of 4 amperes flows in the circuit. This shows a number of relations between voltage, current, and resistance. When we know the voltage and resistance, but not the amount of current, we can tell that the current is 4 amperes, like this. Similarly, we can tell the amount of resistance from the known voltage and current like this. What would you do if you want to know the voltage? You can tell the voltage by multiplying the current by resistance, like this. These relations may be summarized in these 3 formulas. We used a number of parts in our experiments, such as those laid on the panel. Now, let's replace them with symbols. This symbol is used to represent a battery. This is a symbol for a lamp. And this symbol indicates a resistor. This is a switch. And this is an ammeter. This symbol is for a voltmeter. Now we draw an entire electric circuit. Can you tell what is represented by each symbol? Many other parts are also used in electric circuits, and they are indicated by symbols also. When you have a chance, see what other parts are connected in electrical circuits and what symbols are used to indicate them. In this section, we will study how voltage and current changes according to the way resistors are connected to the circuit. First, we connect resistors like this and check the voltage of this circuit. An electric circuit is called a series circuit when resistors are connected in this way. We will measure the voltage at two places. The voltage at the battery is 13 volts. The voltmeter indicates 6.5 volts. The voltage decreases after the current passes a resistor. This is a water model to demonstrate the same series circuit. Water is running through the pipe. The height of the water shows the battery voltage. There are two resistors in the pipe. The flow of current is blocked by these resistors. You can tell from this model how the battery voltage decreases after the current passes a resistor. We check the voltage at these 2 points next. The voltage across the upper lamp is 6.5 volts. The voltage across the lower lamp is also 6.5 volts. And the voltage across the two lamps is 13 volts. We can examine these voltages on the water model. We first measure the height from here to here. Then we measure the height from here to here. We realize from the water model that the sum of the two heights, which is equal to this height, is equal to the battery voltage. Now, we will replace one of the lamps with a lamp having a smaller resistance and continue our experiment. The voltage across the upper lamp with a larger resistance is 8.5 volts. And the voltage across the lower lamp with a smaller resistance is 4.5 volts. The voltage across these two lamps is 13 volts. When resistors are connected in series like this, the lamp having a higher resistance indicates a higher voltage. And the lamp having a lower resistance indicates a lower voltage. The sum of the two voltages is equal to the battery voltage. Now, let's check the amount of current in a series circuit. We check the current at these 2 points. As you can see here, the amount of current is equal at the 2 points. The amount of current is the same at all points of a series circuit. Let's summarize the result of the experiment. The total resistance of a circuit increases as we connect more resistors to the circuit. Therefore, the amount of current decreases. Now, look at a new circuit. A circuit in which resistors are connected like this is called a parallel circuit. We will measure the voltage and current at each resistor. First, we measure the voltage at these 2 points. The voltmeter indicates 13 volts at this point. We have 13 volts here also. The voltage is the same at each resistor in a parallel circuit. Now, let's check the current. We will check current at these 3 points. We place 2 ammeters and see how many amperes they will indicate. Both meters indicate 0.55 amperes. What will the meter indicate for the entire circuit? The meter shows 1.1 amperes for the entire circuit. Now, let's see what will happen when we replace this lamp with another lamp with a higher resistance. The meter indicates 0.55 amperes here and 0.35 amperes here. What will the meter indicate for the entire circuit then? The ammeter shows 0.9 amperes for the entire circuit. Less current flows to a lamp having a higher resistance. And more current flows to a lamp having a lower resistance. When resistors are connected in parallel, the total amount of resistance becomes smaller, and the current is equal to the sum of current that flows through each resistor. We have learned from experiments that resistance increases and current decreases in a series circuit, and that resistance decreases and current increases in a parallel circuit. By checking the voltage, we can tell if a switch is on or off, if a circuit is broken, or if a circuit is shorted. Now we will see the voltage that generates at various points in simple electric circuits. First, we connect a voltmeter and an ammeter at these points of a circuit and see what these meters indicate. The voltmeter indicates 13 volts here. This is equal to the voltage of the battery. Let's check the voltage across the switch. The lamp is not on, but the voltmeter indicates 13 volts. The lamp goes on when the switch is turned on. At the same time, the voltage across the switch drops to 0 volts. Can you tell why? Let's study the same thing on a circuit diagram. When the switch is off, the battery voltage is applied to the end of the red line. Therefore, the voltage across the switch is 13 volts. When the switch is turned on, current flows as shown in the diagram. Since the switch does not have any resistance, no voltage appears, even if current flows there. Now we connect the resistors in series and connect a switch in parallel to one of the resistors. After connecting a voltmeter and an ammeter at these points, we will turn the switch on and off and see what happens. The voltage is 6.5 volts here, and 6.5 volts here also. The ammeter indicates 0.35 amperes. When the switch is off, current flows as shown by the red lines. Since the two lamps form a series circuit, voltage can be measured at 2 points. We turn the switch on next and check the voltage and current. This voltmeter indicates 13 volts, but the other voltmeter shows 0 volts. Can you explain why? When the switch is turned on, current flows as shown in the diagram. Since current flows entirely to the switch, no current runs to the lamp at the top of the circuit, and no voltage appears there. Therefore, the battery's voltage is applied entirely to the other lamp on the right side. The circuit's resistance becomes lower, and current increases in this condition. Let's study this circuit next. What results do you expect from this circuit? The lamp does not go on. We check the voltage. The meter indicates 0 volts. Each battery has 13 volts, and this voltage is applied to both sides of the lamp. But the voltmeter shows 0 volts, since there is no potential difference between the 2 points. Let's go to the next circuit. 4 lamps of identical resistance are connected like this in this circuit. Let's check the voltage at this point first. The meter indicates 0 volts. Can you tell why? Now, let's check the voltage at this point. And at another point. The meter shows 6.5 volts here. The voltage is 6.5 volts here also. As we studied before, there is no potential difference in this circuit, and the voltmeter indicates 0 volts only. Now, we will replace the lower left lamp with another lamp having a different resistance. The meter indicates 9 volts here. It shows 6.5 volts here, and only 2.5 volts here. Since we put a new resistor, painted green in the diagram in the lower left part of the circuit, the voltage changed from 6.5 to 9 volts. The voltage here remains at 6.5 volts. Therefore, there is a difference of 2.5 volts between the 2 points. Whenever there exists a potential difference between any 2 points, the amount of the difference is indicated on the voltmeter. In other words, all values that are measured by a voltmeter are potential differences. The 4 circuits that we just studied show basic principles for measuring voltages. Please become familiar with the different results of voltage measurement at various points of electrical circuits. This brings us to the end of this video presentation. We hope you have fully understood the basics of voltage, current, and resistance, and that you will apply this new knowledge in your daily work.